Hello AP Chemistry and welcome to ionization energy, which is directly tied to everything we talked about in the previous lecture concerning atomic radius, because all of our ionization energy trends are going to be based on atomic radius, okay? Which is why it's really, really important you know those tidbits, because that's all we're going to really use to explain this section. Okay, ionization energy, kind of like the term implies, right? We are going to make ions. Specifically, we are going to make cations. Okay, so anytime we're talking about ionization energy, we are talking about making cations, which means we're talking about removing electrons. Okay, so if we look here, right, that's what we're saying. These are equations that sort of describe ionization energy in that, and it is by definition to remove it from a gaseous atom. Okay, so we are saying that it's the energy required to remove an electron from a gaseous atom, okay, or ion, as the case may be. Okay, now we do say energy required by definition, which means that all of my energy values are going to be positive, right? Because it always costs energy to remove it, right? Because if we think back again to the what's happening in our atom, right? We have an attraction, right? We have our valence electrons that are negatively charged. We have my nucleus, which is positively charged, right? And those valence electrons feel a Z effective. They feel an attraction to the nucleus, right? And every time we break an attraction, that costs energy, okay? Every time we break an attraction, it costs energy, right? Which is why this is going to be a positive number always for ionization energy, okay? So here, right, this would be the first ionization energy of sodium, meaning the removal of the first valence electron, right? This, to form a 2+ ion, would be the second ionization energy of sodium, right? And we could write a third one and a fourth one, so forth and so on. Yes? Okay, now let's go ahead and look at the trends for ionization energy. So if we look here, right, as we go down a group, what typically happens to my ionization energy? Right, as we go down a group, my ionization energy does what? It decreases, which means that as we go down a group, it is easier to remove an electron. Okay, as we go down a group, ionization energy decreases, meaning it is easier to remove an electron. Okay, now if we think back to radius, what did we say happens to the radius as we go down a group? Right, the radius gets bigger. Why does the radius get bigger? Right, because as we add shells, there is a decreased Z effective as we add shells, right, due to shielding and the increased size, or the increased distance of that shell from the nucleus, right? Those outermost electrons feel a decreased Z effective, less attraction, larger size. Less attraction also means it's easier to pull away an electron, okay? As we go down a group, the ionization energy decreases because as we add shells, there's increased shielding, and those valence electrons feel less of an attraction to the nucleus. Therefore, they are easier to remove, okay? Now, as we go across a period, on average across a period, what do we notice? Right, as we go across a period, on average, the ionization energy increases, right? And we'll see that the highest ionization energies are over here with the noble gases, right? Which intuitively should make total sense, right? It should make sense that these are going to be the highest energy to remove an electron from because, right, we already know, and we've been talking about since middle school, that these are a stable set of species, right? They have no interest in losing electrons, right? That serves no purpose for them, okay? So if we're going to put some words to that, right, as we go across a period, the ionization energy increases, meaning electrons are more difficult to remove. And that again goes back to the same explanation we used for the period trend for atomic radii. As we add electrons to the same shell, there is an increased Z effective for my valence electrons and an increased attraction to the nucleus. Therefore, the electrons are harder to remove and require more energy, resulting in a higher ionization energy. Yes? If need be, rewind and play that again. Okay. So anyway, that explains our group trend. Now, as we're looking at this, though, what do we happen to notice? Anything? Hopefully you notice that, look, this is 899. What? This one's only 801. 738, 5 something, 590, 580, blah blah. This one actually fits, and this one actually fits. But here we'll note that there is an exception. Okay? Or an anomaly, we could also say, right? And that doesn't follow our trend because this one doesn't actually go up. Now, if we think about electron configurations, what's the difference as we go from here to here? Right. This closes out my S subshell, yes? As in this is going to be S2, right? S2, S2. This one starts my P subshell, right? So that means, for example, if we're talking about beryllium, right? Beryllium looks like lithium, 2s1, okay? While boron looks like lithium. Oh, that's definitely not what I mean to say. Beryllium says this, right? And this one says 2s2, 2p1, okay? So for beryllium, when we talk about removing an electron, it's from the 2s orbital. When we talk about boron, when we're moving it from the 2p orbital. Thinking back, all the way back to the beginning of the chapter 7 videos, what did we say about Z effective and orbital shape? Right, the s orbital, right, does penetrate closer to the nucleus, right? This one is a little bit further from the nucleus, right? Which means that this electron, right, especially this first p electron, is shielded from the nucleus by this full s orbital, meaning that this Z effective is actually a little bit less than this Z effective, which means that this one's a little bit easier to remove, okay? And again, if need be, rewind, slow it down, and write all that down. Okay, if we look over here, we'll see that, oh look, that also repeats itself over here, and we have another exception over here, right? This one, though, obviously, if we think about, okay, this is P1, P2, P3, P4, right? P1, P2, P3, P4. What makes P4 different than P3? P1, P2, P3, P4, right? Now, thinking back to Hund's rule, right, we spread everything out one per orbital first, and then we go back and pair it because, right, however minutely there is, right, there is some electron-electron repulsion, right? They're both negative charges hanging out in a relatively small shared space, right? Which is why the first of my paired electrons, right, is a little bit easier to remove due to electron-electron repulsion, okay? By here, but the increased Z effective has sort of mitigated that, and that's not really an issue anymore, okay? So those are our ionization energy trends. Here is a little discussion on successive ionization energy. So when we say successive, right, we means the one, the ones that come after, so the second and the third and the fourth and so on, all right? Here we have sodium, magnesium, aluminum, etc., 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 right? So basically here we have all of period 3, okay? And here are their first ionization energies, and they increase across the period, just like we said that they generally do, right, with an exception here, which makes sense because we just explained that, right? And another exception here, which again, we just explained, okay? Now, you'll see that sodium's first IE is about 500, and this one goes up in order of 10. Yes, do you see that? This one goes up in order of 10. Magnesium has 7 something, then it goes up by double, and then it goes up by several orders. Yes? So that would be like 3 or 4 orders. Okay? Actually, that'd be more like 4 plus. Okay, here we have aluminum, first set one, second one, third one, fourth one goes up by probably about 6 orders. Okay? Now, couple of trends to note. One, successive IEs are always greater than the one before. Successive IEs are always greater than the one before. And if we think about it, right, that's because we are increasing Z effective every time we remove one, right? Because then once I remove one, then we look at my protons versus electrons, right? I've increased my Z effective, which means my second one's going to be even higher, my third one's going to be even higher. But there is always a place where that jump is exponential, right? Where that jump goes up by several orders of magnitude, right? So instead of just doubling, it goes up by 4, 5, 10, sometimes even more. And that has to do again with our electron configurations. Once we get to my core electrons, my IE goes up several orders of magnitude, okay? Which if we think about it, right, if we're talking about removing from our valence, that's our outermost shell. And then once we've removed all of those, the innermost shell is where we're going to get the higher ones, because now we're talking about removing from the core, okay? So if you think about sodium has 1 valence electron, so if we remove this one, the next one goes up by a lot. Magnesium has 2 valence electrons, so that third one is going to be really, really high, right? And so forth and so on for the trend, okay? Finally, nope, that is finally, okay. Yeah, okay, I think that's all. All right, thanks for listening. Be good. I'll see you soon. Bye.